In section 6.3, hyperbolas, let's look at the last of our conic sections. Remember, the four conic sections were parabola, circle, ellipse, and hyperbola. So we're looking at the hyperbola. If you recall the hyperbola, that's when the flat surface crosses the double nap cone. It has to cross both naps of the cone, the upper nap as well as the lower nap, in such a way that there are two branches of this hyperbola. Each branch, by the way, looks like parabolic. That's what the hyperbolas look like. The branches themselves individually look like parabolic branches. But hyperbolas are graphs that are actually made up of two parts. Okay, and you can tell from the graph of a hyperbola, just like the ellipse and sideways parabolas, these are not functions. You see that the hyperbolas fail the vertical line test. We could have vertical hyperbolas. These are not functions either. I'm looking at the vertical hyperbola here versus the horizontal hyperbolas. So in either case, these are not functions again. They are simply relations. Now, the definition of a hyperbola, I have it here. A hyperbola is the locus of all points in a plane, the difference of whose distances from two fixed points called foci is constant. The difference of distances. So for example, if you look at d1 minus d2, look at absolute value, because one could be like, for instance, this could be d1, that could be d2. So as long as the absolute value of the difference between the two it's the differences from two fixed points is a constant. So this is going to be equal to a constant, as it's stated here also. All right, so that is a formal definition of a hyperbola. The hyperbola, like the ellipse, it has two foci. That's the center of the hyperbola. And the vertices are right in here. The turning points of each branch would be the vertices. Now, associated with every hyperbola, by the way, is the axis. There's an axis of symmetry. Of course, the axis of symmetry here is both x and the y, x and the y. That's for the hyperbolas that are centered at 0, 0, by the way. The center of hyperbola is right here. Those are the center. Okay. Now, I'll show you how to graph hyperbola, the branches of hyperbola, in just a few minutes. But in order to do that, you see this dotted rectangle that we have here? This is called a fundamental rectangle. The fundamental rectangle. That's what it is, and it is here also. We need that in order to draw the branches correctly of the hyperbola. Okay, and that's what this is. Now, if you draw the diagonals of this fundamental rectangle, both diagonals, the diagonals make up what we call the asymptotes of that hyperbola. Again, neither the asymptotes nor the fundamental rectangle, anything that's dotted that you're looking at, these are not part of the graph. The graph is a solid portion. Okay, the two branches are the graph. But those are simply just the reference points and reference names that we are using. So the equation, what does the equation look like? These are the ones that are again centered at 0, 0. If the denominator of x squared, a squared here, for the hyperbola, we assume a squared is bigger than b squared. In the formula that you see assumes that. Now, if you note, there are actually two equations here that we have, and it's almost look like the equations of the ellipse, with the exception of a plus on the ellipse has now become minus for the hyperbola. Okay, now the denominators, if you look at the denominators, x squared, its denominator is a squared here, but its denominator is actually b squared here. Okay, so those are different. And the reason is because, again, we assume a squared is bigger than b squared here. And primary reason for that is also because subtraction is not commutative, so it makes a difference whether the hyperbola starts with x squared as opposed to y squared. Okay, now the hyperbola that starts with x squared and then it's minus y squared, these would be what we call horizontal hyperbolas. If the equation starts with y squared followed by a negative sign minus x squared, these become vertical hyperbolas. Now, what do I mean by vertical horizontal? Well, if you connect the line segment that connects the vertices, this axis, this line segment, it's called the transverse axis. So for a horizontal hyperbola, transverse axis is horizontal. That's what makes the hyperbola horizontal. And if the transverse axis, remember, that's the segment that connects the vertices. If it's vertical, then we have a vertical hyperbola. Every hyperbola has a transverse axis, and it also has a conjugate axis. The conjugate axis would be this axis that's perpendicular to the transverse axis. In the case of a vertical hyperbola, the conjugate axis is this axis, connects the endpoints of b and negative b together. All right, so every hyperbola has transverse axis and conjugate axis. Transverse connects vertices of the hyperbola. Conjugate doesn't connect anything. Okay, it's just these are points on the fundamental rectangle. So you have the equation, the relationship between ABC. Remember, for the ellipse, it was a squared minus b squared. That was for ellipse. But for hyperbola, it's actually c squared is a squared plus b squared. That's going to be for the hyperbola. And from this, you can see that c squared is greater than both a squared and b squared, because the sum of those becomes c squared. So c squared is larger than either of those individually. And we take a, b, c again to be positive. All right, now these are again hyperbolas centered at 0, 0. The more general case of those are hyperbolas that are centered at hk. And to the right here, by the way, just a thing about eccentricity of a hyperbola. Remember, all of these conic sections have eccentricities. We said for circle, we showed it, eccentricity was 0. For the parabola, we showed it, eccentricity was 1. For the ellipse, we showed it in the previous video or lecture. The eccentricity lied between 0 and 1. Now, the eccentricity of every hyperbola is going to be greater than 1 for the reason that you're seeing here. Definition of eccentricity was a ratio of c to a, and because c again is made up of the square root of a squared plus b squared, and we just mentioned above also, c squared is the sum of the other two squares. So individually they should be less than a and b, less than c squared. Well, if c is greater than a, divide both sides by a, and you get the eccentricity has to be bigger than 1. So here you're looking at 3 possibilities of what the eccentricity, how it affects the branches of a hyperbola, as far as the branches being sort of narrow here, and then the branches are becoming wider and much wider. Okay, so for the case where eccentricity is near 1, the branches are kind of narrow here, right? And as the eccentricity grows, the hyperbola becomes nearly vertical. I mean, like a line almost, like that. These are the hyperbolas with larger eccentricities. Now, the HK form, you're looking at it. Again, notice the minus between them. It is absolutely important. First and foremost, this must be 1. And this one must be 1 also. Okay, if it's not, we have to take measures, usually dividing by something, dividing by a non-number that makes that 1 by its reciprocal, maybe, multiply by its reciprocal, or divide by itself. Anyway, however we do it, we have to have a 1 there. And then note that it's important with a plus. If that was a plus and that was a plus, then we would have an ellipse. So a minus is what makes it a hyperbola. If it starts with x squared and then minus sign, the transverse axis would be horizontal, hence we have horizontal hyperbolas. If you start with y squared followed by minus sign, the transverse axis would be vertical, and hence we have these vertical hyperbolas. Okay, and then you're looking at specifics of the coordinates. These coordinates, I don't have these memorized, by the way. The vertices, foci, and the asymptotes, it's just too much memorization here if I want to memorize everything. So I usually get these all from the graphs. Once I show you how to graph these based on just the equation, and these other things will follow from it. Okay, but nonetheless, that's what it is. Again, A would be the distance on the horizontal. A is distance from center to a vertex. That's A. Okay, to here. C is the distance from the center to a focal point. Okay, and B is the distance from the center to the edge of that fundamental rectangle in the vertical direction. All right. And the last thing would be the reflexive property of hyperbola. Again, all of these had reflexive properties. Remember, for the parabola, the reflexive property was incoming rays will collect at the focal point, at the focus, right in here. That was the reflexive property of parabolas. For the ellipse, the reflexive property of ellipse was incoming rays from one focus will reflect onto the other focus. So if this one hits here, it will reflect over here. And that was the reflective property of ellipses. Now the hyperbola, interestingly, has this reflexive property also. Usually they use these hyperbolic mirrors as you exit, like the parking structures. You may have seen these mirrors that are concave downward, or they're kind of stick out like this. They're mounted in the corner, like if this is the garage, they're usually mounted here like that. You have these convex mirrors, and these mirrors are in hyperbolic form. And the reason is because, interesting property, the incoming rays that hit the surface of the hyperbolic mirror, for example, there you go. They will reflect it across the other branch. It will go through the focal point of the other branch of the hyperbola. Of course, you only have this mirror mounted right somewhere around the near the wall or something. You don't have this. There's no other mirror on the street. It's just the mirror itself is concaved in a hyperbolic form. So that is a reflexive property of the hyperbola. And by now we have looked at all conic sections. So this table will summarize all conic sections. And the orientation of those you're looking at here in this table. So for the parabola, we have either axis of symmetry, horizontal or vertical. And these are the equations for them. And you can see the the graphs of these in figure 26, and this is figure 26, parts A and B. So these two will pick up possibilities for the parabola. So that's what the parabola will look like. Again, we covered parabola in previous section. I believe it was section 6.1. And then previous to this lecture, we looked at ellipses. With ellipses, you have, again, two possibilities. The major axis could be horizontal or the major could be vertical. You have the equation of those. Look at, again, the similarities between the equation of ellipse and a hyperbola. You see that? If you change the plus to minus and vice versa, you go from ellipse to hyperbola and back to ellipse. All right. And notice for all ellipse hyperbolas, it's important to have one on that side. All right, and there we have it. Now let's take a look at some examples here. Okay. All right, so here is an equation, and this is an equation of a hyperbola. How do we know it? Because we have a minus sign, and both of these terms are squared. Note if one of those was not squared, then that would have been a parabola, because only on a parabola one of them is squared, not both of them. And if this the minus was a plus, this would have been an ellipse. Okay, an ellipse, not a circle, because the numbers are different here. If they were both 9, both 25, and a plus sign, then that would have been a circle. Okay, we'll talk about that later, the identification theorem of conic sections later on. But for this one, let's say we want to find, well, we want to graph it for one thing. We want to find the foci, the equation of asymptotes, domain, and range. It's just about everything that we could possibly want. So first, how do I graph it? Remember, it's very important to have one on this side. So first and foremost, we got to divide everything by 225. That's the first thing we need to do. Now, once we divide by 225, well, 9 and 25 are factors of 225. So that's going to work out nicely here. Oops. So this is going to be 25 minus y squared divided by 9 is equal to 1. Okay, so I got that part. Now, once I have this, that's the standard form. The center, first of all, the center of this hyperbola, right off the bat, we know the center is at 0, 0, because in x minus h, y minus k, both of these are 0 in this case. I don't have x and y in parentheses with a number next to them. Okay, so there's the center. Next, I need to decide on a and b. So this would be a squared, that would be b squared. A squared is greater than b squared, so that means the transverse axis is horizontal. So here's how we actually draw this. I'm going to take square root of 25, that's 5. 1, 2, 3, 4, 5. You go right 5. 1, 2, 3, 4, 5. We go left 5. Okay, so we go right 5, left 5. And then square root of 9 is 3, so I'm going to go up 3 and down 3. And this will help me draw my fundamental rectangle. The fundamental rectangle, I'm going to draw this side parallel to the y-axis, has to go through -5, and that side goes right through 5. So there you go. These are the sides of my fundamental rectangle. Remember, they're dotted points because they're not part of the graph. Then I draw the horizontal sides parallel to the x-axis. They got to go through 3 and -3. Okay, so this is -3. Now, once we have the fundamental rectangle, we next draw the diagonals. Okay, and I didn't draw my -3 correctly. I know you got that. I didn't. And this is better, right? That's -3. Now they look symmetric. So there's my fundamental rectangle. Now, once I have that, I'm going to draw the diagonals. So here's a diagonal of 1. And this would be the diagonal of the other one. You see that? So I have drawn the diagonals. Now, once I have the diagonals done, then pretty much I can construct the branches now. Remember, this is a horizontal hyperbola. So I go from the center, which is at 0, to the right 5, out to the edge of the box. On the right, go out to the edge of the box on the left. And then we're going to draw the branches, these parabolic branches. One goes like that, the other one like this. Make sure they don't cross. They do not cross the dotted lines. Okay, they're asymptotic. So that means it's going to go like this. This part of it goes up like that, and the other branch, this side goes, it goes like this. All right, and there we have it. I'll do a much better graph again in Desmos later on when we do the final problem. And there you go. It wasn't that bad, right? pretty easy. Once you have the fundamental rectangle, it's really easy. Now let's get all of the specifics of this one that we had equations for. I said I don't memorize the equations. I get everything from the graph. So remember, A is the distance from center to a vertex. So A is clearly 5, and B is here from the center to the endpoint of the conjugate axis, right? The longer of the two, the horizontal is transverse axis. The shorter one would be the conjugate axis. Okay, so I have those. Now what do I need next? Let's say the foci. The equation that we need for foci is a squared plus b squared. A squared is 25. Remember, don't square that number again because we see it in the squared form. 25 and 9 makes 34. Thus, c squared is 34. C would be square root of 34, which is near 6, right? That's 5 and like 5.7, 5.8. Let me see. Yeah, that's about 5.8. Okay, approximately 5.8. So we have the C. Now, domain and range of the function. Well, this is not a function, it's just an equation. Remember these conic sections, ellipse, circle, and hyperbola, they're not functions. So the domain of this equation, let's say, the domain, x can exist from 5 to infinity, and on the negative side, from negative 5 to the left. So our domain is going to go from negative infinity to negative 5, or union with 5 to infinity. Both 5 and negative 5 are included. That's the domain. The range could be anything. See, those branches can go down to negative infinity and up to infinity forever. So we're going to say that the range is going to be from negative infinity to infinity. All right. The circle and ellipse are the ones that are range bound because, you know, they're closed figures. But parabola and hyperbola, they're not closed figures. All right, so we got the domain, we got the range. Let's do the foci now. The foci is going to be in front of the vertex, so call this F. In front of the vertex, call it F prime. And how do we find the coordinates of the foci? We need to remember distance from C, from center to a focal point. So the foci are going to be at, in this case, plus minus C and 0. And C is the square root of 34, so plus minus square root of 34 and 0. Now again, if you want to enter this into a software or a program, you can't do plus minus. You have to actually write 34, 0, and then negative 34, 0, probably something like that. I put them together as one because I'm not doing this on a computer. So we got the focal points then, the foci. The two of them are plus minus root 34 comma 0. And remember, square root of 34, we said this is about 5.8. So that's what this is. One focal point, that's square root of 34, 0. The other one is here, negative square root of 34 comma 0. And the asymptotes. There is an equation for the asymptotes, but because the line runs through the center, is y equal ax. B, slope is a, y-intercept is 0. So that's just ax. Where, let me just go mx, sorry. Because we have a in here. I don't want to confuse it with the a you get for the hyperbola. Okay, so that's just mx. M being the slope. So the slope, as I go from one point to the other point, from the center to the corner of the box, I'm looking at the rise over run. Okay, so this is my rise and this is my run. Rise is 3 units, so that's going to be 3, and run is 5, so it's 3/5 x. And that's the one with a positive slope. The one with a negative slope is going to be this one, y equal negative 3/5 x. And again, there are formulas in the book for them. I don't like giving you too many formulas, and I don't like them myself either. So there you go. We got the equation of the asymptotes and foci, vertices, and everything. I don't know if I wrote the vertices. The vertices are going to be at plus minus 5, 0. Right? One is here, the other one is here. And we have those. Okay. And I think that's a complete exercise here. That's the one that was centered at 0, 0. Let's take a look at one that is not centered at 0, 0. So let me move this down below and bring this one above in preparation for the next example. So in the next example now, let's say I'm given an equation that is not in standard form now, it's in the HK form. Yes, it would be standard if you consider the HK standard. X plus 3 squared, suppose it's that over 16, minus y minus 2 squared divided by 9 is equal to 1. So this time I put the 1 in there so we don't have to divide by anything. So this is truly in the HK standard form. Now, for this one, let's do everything that we did earlier. First of all, 16 is bigger than 9. Goes with x, so the transverse axis is horizontal. Now, I cannot start from 0, 0 because this one is off center, correct? HK, the center of this one, is going to be at HK, and HK here are negative 3 and 2, right? H opposite of 3, K opposite of negative 2. So I'm going to go to negative 3, 2. That's going to be 1, 2, negative 3, and 1, 2. So there's the center of this hyperbola. Now, from the center along the horizontal axis, I'm going to go square root of 16. So I'm going to go 4, right 4, and then I'm going to go 1, 2, 3, left 4. So these would be 2 points on the fundamental rectangle now. And then square root of 9, that's going to be 3. From the center, I'm going to go down 3 and go up 3. All right, and now I can see the outline of the fundamental rectangle here. Let's draw our fundamental rectangle. A horizontal parallel to the x, parallel to the y-axis. And there you go. We got that nice looking rectangle. Next, we need to do the diagonals, right, of this rectangle. So I'm drawing the diagonals next. The diagonal is going to be this one. And the other diagonal is going to be this one. Okay, so let's see. This was negative 3. And the center, of course, negative 3, 2. So this height is at 2. Okay. Horizontal hyperbola. At this point, I can draw my hyperbola. Go from the center to the edge of the box and draw that horizontal parabolic branch. And we go to the other edge of the box from the center and draw the other one. There we have this one. All right, and that would be the graph of this hyperbola. Okay, let's make this a little bit more like the one above it. Cool. Now, the labels, the vertices are at, here's one. So I went from negative 3 to the right. Remember, I went right 4, so that puts me at 1. So the x component's going to be negative 3. From negative 3, I go to the right and then left 4. And the height is going to be 2. Now, negative 3 plus minus 4. So one vertex is negative 3 plus 4 at 1, 2. The other vertex is going to be at negative 3 minus 4, negative 7, 2. That's this one, right? Negative 7. Cool. Got that one. What else do we need? Oh, the foci. The foci are going to be from negative 3 again. Oh, I need to find c, correct? For the hyperbola, c squared is a squared b squared. A squared denominator of x, b squared denominator of y. Do not square those again. Do not square 16 and 9. We already see these in their squared form. That's 25. Therefore, c is square root of 25. I was going to write and just put 5. Okay, so c is 5. That means the foci is going to be from negative 3, you go to the right, 5. From negative 3, we go to the left, 5. This is going to be negative 3 plus minus c now, and the same height. The vertices in foci and center are collinear. They all lie along the same straight line. The coordinates of the foci are now negative 3 plus 5. That gives me 2, 2. Negative 3 minus 5 gives me negative 8, 2. So those are the two foci that you saw. This would be F. This would be F foci in front of vertex. So there you go. Somewhere in here is F. And somewhere in front here would be F prime. Perfect. And what else do we need? Oh, the eccentricity. I forgot the eccentricity. Let's do eccentricity. Eccentricity c over a, and c was 5. A is square root of 16, 4. So it's 1 1/4, right? 1.25. Notice for a hyperbola, we said eccentricity exceeds 1. So there you go. That's the eccentricity of that hyperbola. Domain and ranges, I get those from the graph. Domain, all possible x's. Well, x exists from 1 to infinity on the positive side, and from negative 7 down to negative infinity, which we actually go in increasing order from negative infinity to negative 7, parentheses, union with 1 to infinity. Okay, again, those are the domain values. Below 1 and above negative 7 in here, there is no graph in here. You see that? So that's why x does not exist there. So if you do pick a number, for example, I don't know, 0, plug it into here, you're going to run into an imaginary solution for y. Turns out to be something that has an imaginary unit in it. Okay, what about the range? Well, the range is all real numbers, right? Because you can see again, this branch can go here forever, that one can go up above forever. So the range is going to be from negative infinity to infinity. And I think the only thing that remains are the asymptotes. Now, for the hyperbola that's not centered at 0, 0, we're trying to find the asymptotes now. Okay, for asymptotes, I'm going to use the slope-intercept form of a line, so I don't have to use the equation. And, or I'm sorry, not the slope-intercept, point slope of a line. I can find the slope, and I have a point. For the point, I'm looking at this, for example. I'm going to use the center as 1 point on the line. Okay, and the slope is easy to find. That's the rise and run. So this is the run, this is the rise, as I go from 1 point to another point. Now the run was from negative 3 to 1. The run was 4. The slope is, the run is 4, rise over run. Change in x is 4, and change in y, as I go from this point to the higher point, the change was we went up 3, This is at a height of 5 now. We went from 2 to 5, so the rise is 3. The slope's 3/4. And there's a formula for it. It's like B over A, whatever that is. So there's my slope. And I'm going to use y minus the coordinates of the center. My point, the point I'm using is -3, 2. It has to be the center, folks, okay? So it's going to be y minus 2 equals slope. Slope's 3/4 x minus x1. And this will give me the equation for the slope is going to be y equal to 3/4 x plus 3 plus 2. Move 2 to the other side. So there you have one. The other one, that's again, that's the one that has positive slant to it. The other one is the one with negative slant, right? It's going to be this line, that line, which goes through the same point center. So the slope of that other one would be, the slope of this one is -3/4. The slope of the one positive is 3/4, that one. We can actually put both lines together, plus minus 3/4 x plus 3 plus 2. And that'll pick up both of them. And the reason, because we're using the same point. The only thing that's changing is the slope, and we accounted for that in our formula here. When you do this process for the line with negative slope, see, that's not going to change, that's not going to change. The only change will be in the slope from positive to negative. And there you have it. These are the asymptotes. And remember, in the word asymptotes, the P is silent. So you don't say asymp. There's no P. Do not pronounce the P. It's asymptote. Alrighty. And we're done with this one. Let's take a look at another one. For this next one, let's say we want to write the equation. We're going to find the center, and we want to determine whether the transverse axis is, say, horizontal or vertical. Okay, so let's do the next one. So here it is. This is the example that we're going to work. Notice this is not in standard form, in the HK form. It is in this polynomial form. Now, going to group the y's again together and factor 25 as I do that. So this is going to be 25y squared negative 10y, and then factor -49 from x squared, and from 392, well, 392 is 8 times 49, and equals 1384 in this one. All right, and next I'm going to complete the square in both x and y. To complete the square, we're going to add half of -10, which is 5 squared, 25. Add half of 8, 4 squared, 16 to the left side. Now, because of the numbers outside parentheses, we got to be mindful of those. So it looks like I added 25 in parentheses, but to this whole left side, I added a multiple of 25 times 25. That's plus 625 on the other side. And it seems like I added 16 in parentheses, which is true, but to that whole left side, I added -49 times 16. Turns out to be negative 784. That's what it turns out to be. Okay, now let's rewrite these. Within parentheses, I have y minus 5 squared, half of -10, -49 times, this would be x plus half of 8 is 4 squared. Don't forget the squares. Without them, the binomial doesn't make sense, because you're exchanging 3 terms for a square of a binomial, so it's got to be squared. Now do the arithmetic on the right side, and we should get 1,225. large number, right? But in a moment it's gonna go down to 1. In fact, let's divide everything on both sides by 1225. Remember, we have to have a 1 on the right side for ellipse and hyperbolas. Therefore, and then divide the common factors. 12, 25, and 25 do have a common factor. Indeed, 49 times 25 is 1225. And x plus 4 squared divided by 25 is equal to 1. And there we have that one. Now, that is the standard, the HK standard form. In this form, we can recognize H and K. So the center is going to be at HK, and the HK in this case, H is -4 and K is 5. Remember, H goes with X, K goes with Y, has to be in the negative form, Y minus K, so K is 5. X plus 4 would be X minus -4. That's why H is -4. So we identified the center of this one, right? The center is at -4, 5. Call this -4 and 5 right in here. Okay, -4, 5. What do I do next? If I want to graph it, because you have y squared minus, so the transverse axis will be vertical. In this one will be vertical. So from -5 here, actually, sorry, -4 and 5. Let me move this down so I can graph it better. -4 is here, 5 would be up. 1, 2, 3, 4, 5. Okay, so that's the center. And you go up 7. Let me do this actually. Otherwise my graph would be too long. So that would be too large. So let's say that's -4 and 5. So I'm going to go up 7. That would be up 7, down 7. And then from this you go right 5, left 5. And we have our fundamental rectangle this way. Right, that would be our fundamental rectangle, and we can do our, it doesn't look symmetric, it's more like this, the rectangle there. I didn't go same amount up and down, that's why. Okay, so from the center again, I went up 7, down 7. So it looks more like a rectangle now. Draw the diagonals like this, vertical hyperbola, right? Because it's vertical, therefore the branches open upward. So those would be the graphs. We didn't want to graph this, I just did it to show you how it's done. So there's the graph, and this is the center. Now we want to determine for this specific one, we just wanted to find the equation, which we did, and we have the center, and the transverse axis is vertical, right? TA, transverse axis, in this case will be vertical. Okay, that's all we wanted to do on this one. Let's take a look at maybe a couple more, and then we'll be done with this video. This next example, let's say this one now, I want to find the equation this time of a hyperbola with the vertices at 0 plus minus 6, and the equation of the asymptotes are going to be, let's say, plus minus half x. In other words, the asymptote goes through the origin. So this is going to be standard form, x squared over well, let's see if it starts with x or y. We don't know that yet, correct? So let me actually graph this roughly enough to where I know whether the transverse axis is horizontal, vertical, or vertical. So the vertex or the vertices are at 0 plus minus 6, call that 6, call this negative 6. Remember, because the vertices are they're on the y-axis, so the parabola has to open upward, right? And downward from here. Well, opens up from the 6, down from negative 6. Therefore, the equation of this hyperbola is going to be x squared over b squared minus y squared. Oh, we started with y, sorry. It's vertical transverse axis. So it's going to be y squared over a squared minus x squared over b squared equals 1. Okay, and this is the transverse axis again. Vertical, so it starts with y. The center is at 0, 0 because y equal mx plus b. This is 0. So the line runs through, what you call it? It runs through the origin, the center. And there you have it. Which made me write h and k here. h, k are 0, 0. Center at 0, 0. Now, what else do we need here? Well, we have the slope, right? So I can now set up, I know my a, by the way. A is 6. So far, I know that's y squared over 36, right? 6 squared minus x squared over b squared equal 1. We just need to determine b, and that's where the slope comes in. And in this case, there you have it. This is like a rise, and this is the run, correct? The rise is 6. We need to know the run. We were given the slope, right? The slope is a half, which is rise. Rise is 6. Run is x. From this, x is 12. Therefore, my b is 12. B squared would be 144. And there, that's how I get the equation of this hyperbola. Just to tidy up this thing, remember this is a equals 6, and this one would be b equals 3. And we found the equation. That's what we want to do. We just want to find the equation. But notice the graph, by the way, helps me quite a bit. So I recommend doing this while you graph the hyperbola. Now let's look at this this next one. Will be the last one that we are looking at. And let's say I want to find the equation of a hyperbola. Last example. We want to find the equation of a hyperbola. This time the center is going to be off the origin. Let's make it at 1, -2. And let's say we are given the foci, or one focus, just one. A focus is at -2 and -2. And we're given a vertex at -1, -2. So we're given all of those detailed informations. And I'm going to move this down. We'll talk about that in a few minutes. So if I draw my hyperbola with information that I'm given so far. Center at 1, -2. So call this one this -2. That's the center. Okay. The focal point is at -2, -2. That's -2, -2. This is where F is. This was the center. That's the center. And -2, -2 is the focal point. Okay, and we were given a vertex at negative. Oh, wait a minute. Center is at 1, -2. So sorry. And here's 1. There we go. So this is going to be 1, -2. X is positive. That's -2. All right, the vertex is at -1, -2. Now this helps. And this is the vertex at -1, -2. And because again, vertex, center, and foci, or a focal point in this case, these are all collinear points. And turns out that and focus is in front of the vertex, so this branch has to open to the right, to the left, right? Otherwise, focus will not be in front of the vertex. And this was the center distance from vertex to a center, right? That's what A is. And this is at -1, this is 1. So our A is 2, right? We take it to be positive. Therefore, A squared is 4. And the distance from the center to a focal point, that's C, right? That runs from 1 to -2. So that distance is 3 units. C is 3. I'm getting that directly from the graph. C squared is 9. Okay, so we got our AC. We can find B now, right? Remember, for the hyperbola, C squared is A squared plus B squared. So that means B squared is C squared minus A squared. In this example, C is 3, that's 9, minus A, we said, is 2, squared was 4. So B squared is 5. Okay, and now because the center is at 1, -2, we're going to have to use the HK form, right? But we got the thing that we needed here for this one. And our equation is going to be in the form x minus h, horizontal. Transverse axis is horizontal because the hyperbola opens to the left and right. And the other one is 3 units over. From 1 you go to 4. This is the other branch, right? And not to confuse, this center is at 1, -2. Okay, so it's x minus h squared over a squared minus y minus k squared over b squared is equal to 1. All right, and we can now actually write the full equation here. It's going to be x minus h is 1 squared divided by a squared, which was 4, minus y minus k minus minus is positive 2. Right, it's minus 2 squared divided by b squared is 5 equals 1. And there we have the equation. And this one's again, for this one again, transverse axis is horizontal. All right, we can find the eccentricity. Since we haven't done much of an eccentricity here, let's do that one. E, the ratio of C to A. We always take A, B, C to be positive. C is 3, right? C is 3 and A is 2. The ratio is 1.5, which is greater than 1. For all hyperbolas, eccentricity is bigger than 1. Which brings us to this very last thing I've been pushing out of my way for the last 30 minutes. So here's a summary of eccentricities for the 4 conic sections. For a circle, eccentricity is 0. For parabola, eccentricity 1. Hyperbolas have eccentricity that exceeds 1. And for the ellipse, they have to be between 0 and 1. And you can see that eccentricity is going to be positive anywhere between 0 to infinity. In general, eccentricity lies between 0 and infinity, because in a hyperbola greater than 1 means infinity. But seldom we work with infinity on eccentricities. That's when the branch of the hyperbola becomes almost perpendicular, or almost vertical, not perpendicular, but vertical. And that's it. That's all we wanted to talk about, and all you wanted to know about hyperbolas are here. As always, thank you for watching, and we are done with this video. Thank you.